So I'm Freddie, and I'm a senior research fellow at Oxford University, working on machine learning for remote sensing and Earth observation. I'm also part of the Frontier Development Lab, and actually the part of the work that I'm going to talk about was run as a challenge, as a research sprint, quote unquote, as part of the FDL annual summer program that lasts 2 months from mid-June to mid-August. And the aim of it is to combine experts from the domain side and also from the machine learning side to solve problems in earth science, space science, and so on. So for instance, the project I'm going to talk about in the end is from earth science perspective, using very high resolution data with partnership with Planet. So the content also here is provided by Gonzalo, who's another FDL researcher, Kristen Clow, Ramesh Nair, and Giovanni Marcisio from Planet. Now, I will talk about two workflows here based on Planet imagery that is not only high resolution, very high resolution spatially, but also temporally, daily, in fact, cadence. One application is on the monitoring of urban growth in high-risk flood areas, and the other one will be the mapping and monitoring of the intermittency of water streams. Now, for the first application, I'm going to give you the big picture. So we estimate that by 2050, more than 2/3 of the world's population will be living in cities, right? So, and the majority of this growth will be occurring in developing countries. And organizations like the World Bank expect to want to advise like 5,000 cities in Africa on urban planning. But the problem is that because local governments are flying blind without this vital data, any kind of unplanned growth would only put pressure on critical municipal infrastructure, right? And this is only exacerbated by the increased flooding caused by climate change. So what Planet did is they computed the change in urban areas from mid-2017 to early 2019 for 5 cities. Addis Ababa in Ethiopia, Bamako in Mali, forgive my mispronunciation, Bangui in Central African Republic, Casablanca in Morocco, and Ouagadougou in Burkina Faso. And they selected cities in Africa with varied climates and terrains, but also such that they intersect high-risk flood zones. And these images also have low cloud coverage. Now, I'm showing you here the process of by using the city of Bangui as an example in Central African Republic. So what they do is they use a variant of the unit, which is a famous now box standard semantic segmentation deep neural network, to map the building footprints in the Planet RGB imagery. And the training data set is compiled from a globally diverse set of geographies, seasons, terrains, something that helps a model generalize very well when you apply it in other scenarios. The PlanetScope imagery is 30-meter resolution, I forgot to mention. And what you see here is monthly mosaics over a period of 20 months over Bangui city. Now, these are nearly cloud-free images compiled from multiple days by doing some forward and backwards infilling. And here you see the corresponding results from the unit building segmentation for the entire city of Bangui in October 2017. And this is for the same, but for March 2019. So if we take the first snapshot and the last snapshot, and then we do a diff, like we do with GitHub, we can see here like the difference in urban growth. And then we see where that overlaps with the high flood risk zones. And by the way, the high flood risk zones are available, third-party data available from FM Global. This is fmglobal.com, which is kind of like a useful tool if you want to see where those flood maps exist in vector data formats. I can provide the link later in the chat. So here's like what the process looks like also in the other cities, Addis Ababa, Bamako, Casablanca, and Ouagadougou. And you can see like the takeaway here is that by using automated analysis of up-to-date satellite imagery, it's possible to quantify urban area growth in any major cities in Africa. And we found that an alarmingly large rate of these cities, in fact, were inside high flood risk zones, and also that these areas were growing, which goes back to the flying data blind. And now to the second application. Now I will show you a second workflow that also benefits from daily, very high resolution imagery. But now this is for the monitoring of water streams and their intermittency. And we call this process, this workflow, we call it pixel streams, meaning from pixels to reach level, stream level information. Now, such an application can inform policy, but it can also improve our understanding of generating stream networks. Here you see the AOIs that we applied, various basins in the United States. For each AOI, the different modalities that we gathered are data from optical satellite, as such from PlanetScope, but also from LiDAR sensors. That we have LiDAR-derived derivatives from aerial LiDAR sensors. So this is coming from the national, I believe it's called National Elevation Program run by USGS. And also this data, the LiDAR data is available for free on AWS or Azure or Google Cloud, you name it. Okay, so the first set of areas, here we select these areas, and in these AOIs, water can be observed in the majority of the streams, and they have different topographic and climatic conditions. And the smallest of streams is usually covered by canopies. This is the main challenge of this work. That's because canopies project shadows, but also we get shadows from steep topography and other types of tall vegetation. Now I'm going to take you through the individual steps of this pipeline. How do we go from pixel level information, water, to the reach level? So here you see a simple satellite image in false color. And this is a typical false color combination of bands that emphasize the presence of vegetation. But here is the corresponding water segmentation of the unit, kind of very similar architecture that you saw earlier for building segmentation. But this particular one fuses the optical imagery of PlanetScope with the LiDAR-based derivatives to give us a per pixel probability of there being water or not. So actually, you see not only the flowing water body, but you also see the static water body there from various ponds. But you also see the little tributaries there branching out. Now, from the LiDAR data, we can derive a raster of the digital surface model, where each pixel here represents the height of the terrain. So this is also known as the bare earth DEM, bare earth for the fact that the heights from vegetation are removed. This is just for illustration, but another derivative is the height of the vegetation only. So you can just simply add those two things and you just get the height of the first return from the LiDAR lasers. And from the bare earth model, what you can do is you can derive the vector data of where water can physically flow, just to give you a very crude explanation of what's going on. And based on where the flow lines branch out, this can be broken down into segments, or as we call them, stream reaches. Okay. And now that we know the location of each reach, because these things are georeferenced, we can aggregate the water segmentation estimates by the neural network to basically give us a map of the percent that is covered, of the reach percent that is covered by water. So now we'll go from the pixel level to the reach level. This is what I meant. But this is just based on a single day, right? Remember that we have daily imagery. So what happens if we repeat this pipeline daily? Now let's see if this plays. Okay, so as you can see here, if we repeat this daily, we get a georeference time series of water coverage at the reach level. This daily PlanetScope imagery, the takeaway is that it enables this wet reach identification over time. There are shadows that are cast from the walls of the small canyons, causing some false positives. but also we see some false activity happening because of the snow. So this model was not trained on rare seasons. There's no way to differentiate between snow and water. The variability is greatest along the smallest tributaries of the Seine, as well as along the banks of the larger river, which is exactly what we would expect. But the big takeaway is that such time series will not only allow us to update and expand our situational awareness of stream networks at near real time, but over time we can also characterize the intermittency of surface flow of each stream. Furthermore, in the future, with that kind of byproduct, one could correlate this time series with other parameters, such as rainfall, to help forecast the stream flow, if forecasting was of interest. To understand the level of improvement that very high resolution imagery can buy us for water mapping, here's an example compared with the state of the art in water mapping based on Landsat 8 imagery from a Nature paper in 2016. So you can see clearly the qualitative difference in the capacity of water mapping, where now we can not only map this very small stream that wasn't possible before with Landsat 8, but you can see the little bodies of water, static bodies of water. In summary, the global availability of satellite imagery and the power of deep learning-based models, which generalize across diverse terrain given the right amount of training data, means that this approach can be applied across widely varied terrains and at a planetary scale. Thanks for your attention, and I'm happy to answer any questions in the chat.
Yes, thank you very much for this very interesting talk and also the very nice animations. Yes, are there any questions? So please, again, I would suggest if there are questions, just go ahead and unmute.
Well, I'll kick it off, as it's sometimes
Okay.
some of the start
Yeah.
things. A very simple one, and I hope you didn't cover it and I just missed it, but what's the minimum width of stream that you can detect with this, Freddie?
Yeah, that's a good question. So if we were to simply rely on optical imagery, so there, I think a very one intuitive answer is just think about the Nyquist rate, the Nyquist limit. If your ground sampling distance of a pixel is PlanetScope is 3 meters, then it's impossible to resolve anything, any differences of stream width that are below 6 meters, right? When actually what we start to observe is that the performance starts to degrade for any streams that are below that type of width. So any stream that is below 6 meters, most of the time we fail to capture it. That said, there are other cues also available from the satellite imagery. Sometimes the model is able to pick up the presence of water through vegetation, the presence of vegetation. And there are other cues sometimes that are very non-intuitive that you might not expect. Sometimes the models also find shortcuts, ways to cheat. But what is interesting is that when we complement the data fusion of optical data along with the lighter based products, something like the DEM, which tells you basically where, kind of gives you the model an idea where water could flow. And that product comes at 1 meter resolution, I should mention, then things do improve very much. But again, there's a limit. I think the big bottleneck is because the smallest ones are more likely to be covered fully by shadows, and they usually go through small canyons and such. The shadows are basically a confounder, and the model has no way to differentiate whether the shadow in the small canyon is flowing water or is just because that time of day it happened to be shadowed. That's the biggest challenge that we have. But one way they're actually working on this now is we actually use the terrain data, and we can create hill shades, very detailed hill shades, if we know the timestamp of acquisition from the PlanetScope constellation. So this is just a matter of knowing how to query the API. You can, if you know what tile every pixel comes from, it can tell you also the timestamp. So given the time, you can generate the sun's elevation and azimuth, and then from that we can generate the right hill shade. So the model can now differentiate, can know where to expect a shadow. You can create a kind of a soft shadow mask. This is one approach. This is one direction we're going towards.
Okay. Thank you. I have lots of other questions as well, but I want to let other people have a chance. and actually, what we want to do now is just kind of open the discussion up to questions to any of the presenters who are still here. Even if they're not here, actually, you know, we can have a discussion around any points of interest. So, you know, I just will take the opportunity to say thank you to everybody, because I think it's been a fantastic set of presenters all afternoon. Really top class stuff, really exciting stuff. It's got me itching to go and do some more research and try and collaborate with probably most people who presented this afternoon. But yeah, I'll be quiet now and let other people ask some questions, start some discussions.
I'm seeing one question at the chat. Any applications for this approach to understand water abstraction effects on the streams? Can you? I don't know what you mean by water abstraction. I'm a machine learning guy, not a hydrologist. Is that a thing?
Is Bruno here to ask? I mean, water abstraction means, you know, where they're taking water either directly from the river or, you know, it's quite a big problem in the UK, is actually streams drying up due to abstraction, which is more commonly from groundwater. But if they're kind of spring-fed river systems, you suck water out of the ground, and it, you know, it has an impact on where the streams will flow. So I think that's probably what the question refers to. And that was what motivated my question, really. There's quite a lot of effort put into trying to understand where the intermittent streams are flowing in this country. And if we could do it with, you know, high resolution and high repeat rate, high revisit rate satellite imagery, then it could be a very effective way to do that.
Yeah, I think that's a very important question. Like, basically, you know, the elephant in the room is that obviously this is only the water that you see, right? Only surface runoff, and it doesn't really, because if we care about the intermittency of the streams, it's important to know also the groundwater level, right? So I guess if anything, maybe it can help if coupled with something like a water model, national water model, for instance, in the UK or in the US, where they use a simulator model to basically like tell you how much rainfall exists. You know how much rain falls, you can see how much water is flowing. So I guess you can probably remove some first order effects, and then you can make some inferences about the groundwater. This is just a conjecture, I don't know. Another question: does satellite pass often enough to use this for flood forecasting by looking at increase with rivers in regions? Yeah, so this PlanetScope data, this comes in by design. These orbits are allowing for a daily global coverage of the planet. So yeah, anything that can be resolved with 3 meters of ground sampling distance, I think, and especially I think when you talk about floods, probably we're talking about larger bodies of water. So there obviously that could be an ideal application of this type of product.
Is the PlanetScope data available for free, Freddie? Because I know they do high resolution stuff that isn't. But
well, I mean, it is a commercial product, right? So I think the offering is by default you have to pay for this stuff. But that said, there are they do open some data for scientific applications. So I think there's like an open data program that you have to apply for, and I think they kind of treat it in a case-by-case basis. But you know, for our case, because we wanted like 2 years worth of daily data for this AOIs, talking about 20 terabytes of imagery, they don't just hand it over like that. I think there needs to be a need, but it is a logistically difficult thing, right? You know, because like if you want to do this daily fashion and you want to prove a proof of concept that if you are to deploy this is what you need to do. This is what kind of data you need to process. The starting point is, okay, let's take let's say 2 years for those small AOIs. Let's prove that this can be done. And then we can think about how we can stream data in a daily fashion.